Okay, so here is the formula, and this is the full-fledged formula for power emission. It's exactly the same as the other formula, only now we've added something called an emissivity. And the idea of emissivity is its ability to emit radiation, right? Surfaces that are shiny tend to have very low emissivities, and ones that are sort of dull and black tend to have a very absorptive one, right? So rusted iron is very absorptive. Soil is very absorptive. Black paint is very absorptive. Ice, oh, well, ice absorbs a lot too. Huh? That's interesting. Snow, though, is a little less. Interesting. Okay. Mercury is very, very shiny, right? So it's got a very low emissivity, right? Okay. And then let's see, a person has a body surface temperature of 35 Celsius and is in a room where the walls are at 14 Celsius. If they have a surface area of 2 square meters and an emissivity of 0.57, what is the net rate of heat lost to the room? Okay, so what we're going to do is we're going to go power radiated minus the power emitted, right? So power radiated, right, minus the power absorbed. And it's all absorbed over this area with that emissivity. Apparently, I just looked that up. Who knows? Human flesh, 0.57, right? Okay. And that'll be the net rate of heat lost, right? So that's going to be emissivity sigma area temperature of the person, right, to the fourth minus emissivity sigma area temperature of the person, I'm sorry, the room, let's make that R, right, to the fourth, like that, right? Okay, well, if you look at that, everything's the same. The emissivity will be that, the sigmas are, of course, always sigma, and then the area will be the area, the 2 square meters, right? Okay, so this is ultimately going to be emissivity sigma area, and then we just subtract those temperatures, right? Temperature of the person to the fourth minus the temperature of the room to the fourth, right? So let's plug it in. So we go 0.570, and this is a pure number, just like I don't know, a coefficient of friction, but we didn't study that. Okay, so let's see, and then times 5.67, right? Times 10 to the minus 8th watts per square meter Kelvin to the fourth, right? Times the area, which is 2 square meters. That's about right. Your body has about 2 square meters of stuff, of skin, right? Okay, let's see. We got to figure this out. So 35 degrees Celsius, 35 plus 273.15. Thought you'd get me with that. That's 308.15 kelvins. And this one here is 14 plus 273.15. I've got to turn these into kelvins, right? 287.15 kelvins, right? So I've turned that into kelvins, this guy into kelvins. Now we're all set, right? So 308.15 to the fourth minus 287.15 to the fourth. And they do this, they never do it with like people in a room, but they do this with like the Earth emits energy into space, but space emits energy to the Earth, right? Or the atmosphere, more likely, right? So 0.57 times 5.67 e to the minus 8 times 2 times parentheses 308.15 raised to the fourth minus 287 raised to the fourth. I get 143.36 watts. They're playing cards up in the front of the room. That's what they're doing. This is a physics party going on here. That's what you're hearing. So that's an unnecessarily complicated example.